When sizing a conductor on a 120/240 volt single-phase 3-wire transformer, the 240 volts voltage is used to divide the kVA by to find the current value because the transformer's output voltage is 240 volts. The kVA rating of a transformer is determined by its output voltage and current. In this specific situation, the transformer's output voltage is 240 volts, so the kVA is divided by 240 volts to find the output current. The output current is then used to size the conductor. The conductor must be able to carry the output current without overheating. The larger the output current, the larger the conductor that is required. If the 120 volts voltage were used to divide the kVA by, a higher current value would result. This is because the 120 volts voltage is the voltage between one of the output terminals and the neutral terminal. The current that flows through the conductor is the current that flows between the output terminals, which is twice the current that flows between one of the output terminals and the neutral terminal. Therefore, using the 240 volts voltage to divide the kVA by gives the correct current value for sizing the conductor. To reiterate, the core reason for using 240 volts instead of 120 volts in this calculation stems from understanding where the power is being delivered in the system and how the transformer is designed to operate. The transformer is set up to provide 240 volts across its two hot legs. This 240 volts potential difference is what drives the current through the load connected to both hot legs. The kVA rating, which represents the apparent power the transformer can supply, is based on this 240 volts output. To find the total current the transformer can deliver at that voltage, the kVA is converted to volt amperes and then divided by the voltage. This calculation yields the rated current, which is crucial for selecting a conductor that can safely handle that amount of current. Using 120 volts would only give the current in each leg, and that is not what is used. The 240 volts is what you want to size the conductors from. Think about a simple analogy involving a water pump and a pipe. The pump represents the transformer, the water pressure represents the voltage, the water flow represents the current, and the pipe represents the conductor. The pump is rated to deliver a certain amount of water flow at a specific pressure. To determine the size of the pipe needed, you need to know the total water flow the pump can handle. If you only consider the pressure and flow in a small section of the pump's outlet, you won't get the correct total flow, and you might end up with a pipe that's too small. In the electrical system, the 240 volts represents the total pressure the transformer is applying, and the rated current represents the total flow of electrical energy. Using the 240 volts in the calculation is like considering the total pressure and flow of the pump, ensuring you select the correct pipe size, or, in this case, the correct conductor size. It is important to remember that safety is paramount when working with electrical systems. Always consult relevant electrical codes and standards such as the National Electrical Code, also known as NEC, to ensure proper conductor sizing and installation practices. This ensures a safe and reliable electrical system. Additionally, consider factors such as ambient temperature, conductor insulation type, and installation method when selecting conductors, as these factors can affect the conductor's ampacity, which is its current carrying capacity. Also, never assume that a conductor is properly sized. Always double-check the calculations and verify the conductor size before energizing a circuit. Proper conductor sizing is crucial for preventing overheating, voltage drop, and other potential hazards. Using the correct voltage for calculations is a foundational concept in electrical engineering, impacting the safety and efficiency of electrical systems. Firstly, the 120/240 volt single-phase 3-wire system is a common configuration used in residential and light commercial applications. It consists of two 120 volt lines that are 180 degrees out of phase with each other and a neutral wire. The voltage between the two hot lines is 240 volts, while the voltage between either hot line and the neutral is 120 volts. Secondly, the transformer in this system steps down the higher voltage from the utility company to the lower 120/240 volts level suitable for use in buildings. The transformer is rated in kVA, which represents its apparent power capacity. Apparent power is the product of voltage and current, and it is expressed in volt amperes or vol or kilovolt amperes kVA. Thirdly, when sizing conductors, the goal is to select a conductor that can safely carry the expected current without overheating or causing excessive voltage drop. The National Electrical Code, also known as NEC, provides guidelines for conductor sizing based on the ampacity of the conductor. The ampacity is the maximum current a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. Fourthly, the calculation for determining the required conductor size involves several steps. First step is to determine the load that the conductor will be supplying. This is typically done by adding up the volt-ampere ratings of all the equipment and devices that will be connected to the circuit. The second step is to apply any applicable demand factors or diversity factors to the load. Demand factors are used to reduce the calculated load to account for the fact that not all loads will be operating at the same time. Diversity factors are used to reduce the calculated load to account for the fact that not all loads will be operating at their full rated capacity. The third step is to calculate the minimum conductor ampacity required. This is done by dividing the calculated load in volt amperes by the voltage of the circuit. For a 120/240 volt single-phase 3-wire system, the voltage used for this calculation is 240 volts, as that is the voltage across the two hot legs that supply the majority of the power. The fourth step is to select a conductor with an ampacity equal to or greater than the calculated minimum conductor ampacity. The NEC provides tables that list the ampacities of various conductors based on their size, insulation type, and installation method. The fifth step is to adjust the conductor ampacity for ambient temperature and other conditions of use. The NEC requires that conductor ampacities be adjusted for ambient temperatures above 30 degrees Celsius, also known as 86 degrees Fahrenheit. The NEC also requires that conductor ampacities be adjusted for the number of conductors in a raceway or cable. Fifthly, using the 240 volts voltage instead of the 120 volts voltage in a conductor sizing calculation is essential for ensuring that the conductor is adequately sized to carry the expected current. If the 120 volts voltage were used, the calculated current would be higher, and a larger conductor would be required. However, this larger conductor would not be necessary, as the actual current flowing through the conductor would be less than the calculated current. Sixthly, the neutral conductor in a 120/240 volt single-phase 3-wire system carries the unbalanced current between the two hot legs. If the loads on the two hot legs are equal, the neutral current will be zero. However, if the loads are unequal, the neutral current will be equal to the difference between the currents on the two hot legs. The NEC allows the neutral conductor to be smaller than the hot conductors in some cases, but it must still be sized to carry the maximum expected unbalanced current. Seventhly, in addition to conductor sizing, it is also important to consider voltage drop. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that voltage drop be limited to 3% for branch circuits and 5% for feeders. Eighthly, to minimize voltage drop, conductors should be sized as large as practical. The NEC provides formulas for calculating voltage drop based on conductor size, length, and current. Ninthly, it is also important to consider the type of load that the conductor will be supplying. Some loads, such as motors, require a larger conductor than other loads, such as lighting. This is because motors draw a high inrush current when they start up. Tenthly, the NEC provides guidelines for sizing conductors for various types of loads. The NEC also provides guidelines for sizing overcurrent protection devices, such as circuit breakers and fuses. Overcurrent protection devices are designed to protect conductors from overheating and damage due to excessive current. The overcurrent protection device should be sized to protect the conductor, but it should not be so small that it trips unnecessarily. In summary, Sizing conductors on a 120/240 volt single-phase 3-wire transformer requires careful consideration of several factors, including the load, voltage, ampacity, voltage drop, and type of load. The NEC provides guidelines for conductor sizing and overcurrent protection, and it is essential to follow these guidelines to ensure a safe and reliable electrical system. When dealing with electrical systems, adherence to safety standards is paramount. Always consult the most recent edition of the National Electrical Code, also known as NEC, and local electrical codes for specific requirements and regulations. Engage a qualified electrician for installation, repairs, or modifications to electrical systems. Improperly sized conductors can lead to overheating, insulation breakdown, and potentially electrical fires. Overcurrent protection devices, such as circuit breakers and fuses, should be properly sized to protect the conductors from overloads and short circuits. Regular inspections and maintenance of electrical systems can help identify potential problems before they become hazardous. Ensure that all electrical connections are tight and corrosion-free. Avoid overloading circuits by plugging too many devices into a single outlet or circuit. Use surge protectors to protect sensitive electronic equipment from voltage spikes. Grounding is a critical safety feature that provides a path for fault current to flow back to the source, tripping the overcurrent protection device and preventing electrical shock. All electrical equipment and systems should be properly grounded. Ground fault circuit interrupters, also known as GFCIs, are designed to protect against electrical shock by detecting ground faults and interrupting the circuit. GFCIs should be installed in areas where there is a risk of water exposure, such as bathrooms, kitchens, and outdoor locations. Arc fault circuit interrupters, also known as FSIs, are designed to protect against electrical fires by detecting arc faults, which are dangerous electrical discharges that can occur in damaged or deteriorated wiring. FSIs should be installed in bedrooms and other areas where people sleep. Working with electricity can be dangerous, and it is essential to take precautions to protect yourself from electrical shock. Always turn off the power at the circuit breaker before working on any electrical equipment or wiring. Use insulated tools and wear rubber gloves and safety glasses. Never work on electrical equipment or wiring when you are wet or standing in water. If you are not comfortable working with electricity, hire a qualified electrician to do the work. Electrical safety is a shared responsibility, and it is essential to educate yourself and others about the hazards of electricity and how to prevent electrical accidents. By following these safety guidelines, you can help ensure a safe and reliable electrical system for yourself and others. It's also important to remember that electrical codes and standards are constantly evolving to reflect new technologies and safety concerns. Stay updated on the latest changes and revisions to the NEC and other relevant standards. Participate in continuing education courses and training programs to enhance your knowledge and skills in electrical safety. Share your knowledge and experiences with others to promote a culture of safety in the electrical industry. By working together, we can create a safer environment for everyone. The information provided is for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician for specific recommendations and solutions for your electrical needs. Local regulations can vary and may require specific permits for electrical work. Check with your local building department or electrical inspector for any applicable requirements. When selecting electrical equipment and materials, choose products that are listed by a recognized testing laboratory, such as Underwriters Laboratories, also known as UL, or Electrical Testing Laboratories, also known as ETL. Listed products have been tested and certified to meet safety standards. Ensure that all electrical equipment and wiring is properly labeled and identified. This will help prevent confusion and errors during installation, maintenance, and troubleshooting. Keep electrical panels and equipment accessible and free from obstructions. This will allow for easy access in case of an emergency. Develop and implement an electrical safety program for your workplace. This program should include training, procedures, and inspections to ensure that employees are aware of the hazards of electricity and how to prevent electrical accidents. Encourage employees to report any electrical hazards or concerns to management. Promptly address any reported issues to prevent potential accidents. Regularly review and update your electrical safety program to ensure that it remains effective. Electrical safety is an ongoing process that requires continuous attention and improvement. By embracing a proactive approach to electrical safety, you can create a safer and more productive environment for yourself and others.